Today we are going to discuss about heap trees or priority queues. That is the study of min heap and max heap. First of all, what is a heap tree? A heap tree or priority queue is a collection of elements such that each element has an associated priority. Priority queue is a data structure like stack and queue where insertions and deletions and retrieval is done based on priority. A priority can be either maximum or minimum. Priority queues are implemented using heap tree or binomial queue. In here we are using heap tree. A heap is a hierarchical data structure in which operations are done on maximum or minimum priority. A binary heap is defined as a binary tree with two additional constraints such that shape property, heap property. So shape property means the binary tree should be like a complete binary tree means the elements of the binary tree are filled level by level from first level to last level, that too from left to right. Then heap property. It contains either min heap or max heap. Min heap means parent value is less than children value. Max heap means parent value is greater than children value. See here, max heap. This is a max heap. A binary tree which is treated as a max heap, and one more binary tree which is treated as min heap. Both are binary trees. One is max heap, the other is min heap. In max heap, see, root value is 5. It is having left child and right child. Both are less than parent value. Again, left and right are binary trees and max heap. So again, see, in the left subtree, 4 is root, 4 is greater than its children, 2 and 1. In the same fashion, in min heap, root value is smaller than its children value. 1, 1 is less than 5 and 4. Again, left and right are min heaps. 5 is root of left tree. 5 is less than its left value and right value. And 4 is less than its left value and right value. Everywhere it follows the same rule. So min heap means parent value is smaller than children value, and max heap means parent value is greater than children value. Let me explain creation of min heap with following node values 5, 4, 7, 3, 2, 10, 11. So minimum heap, we are going to construct a minimum heap. So the property of minimum heap or any heap tree should be, it should satisfy shape property and it should satisfy heap property. Shape property means it should be a complete binary tree. It should be a complete binary tree. Heap property means we are going to construct a minimum heap. It should satisfy min heap property. Min heap property means parent should be less than children. Complete binary tree means the elements of the binary tree should be filled from level by level. That too, nodes has to be filled from left to right in every level. Initially, we assume that there is an empty heap, empty heap tree. We try to insert first element, insert 5. So first node is inserted and that becomes root. So it is not having any children. First level, that is level 0, element is inserted as root element. It is not having any children. So it is following, it is satisfying shape property and it's satisfying heap property also. Shape is a complete binary tree, heap is a minimum heap. There is no question of comparing with any other element. So it is a minimum heap. Now try to insert one more element. Insert 4. So the new element is inserted at the end of the heap. So next possible location is left of 5. So 5 is root value and we have inserted an element at left of 5. So it is a heap tree. But we have to check whether it is satisfying both the properties, shape property and heap property. What is shape? Yes, it is a complete binary tree. Shape is okay. What is heap property? Is it satisfying heap property? Heap is minimum heap. So parent should be less than children. So it is not satisfying. To make it satisfying, these two values are interchanged. Parent and child values are interchanged. So interchange these two values. So 4 and left of 4 is 5. Now root. See, now it is satisfying shape property. It is a complete binary tree. Heap property, parent is less than its children. So yes, it is satisfying heap property. So it is a minimum heap. Now try to insert 7. Insert 7. 4, 5. A new node is inserted at the end of the binary heap. 7. 4 is root. 4 is root. Now check. We have constructed a binary heap. It is whether it is satisfying shape. Shape is a complete binary tree. What about heap? Parent should be less than children. 4 is less than 5. 4 is less than 7. Yes, it is satisfying shape property as well as heap property. So it is a minimum heap. Minimum heap. Next, insert other value. Insert 3. Insert next node 3. We insert new node at the end of heap. 4, 5, 7. In the next level, starting value will be our new element 3. So 3 is inserted as left of 5. Now we have to check. Is it satisfying shape? Yes, shape is a complete binary tree. What about heap property? Is it satisfying min heap property? No, because see 4 is less than 5, 4 is less than 7, but 5 is not less than 3. So you have to interchange these two to make it satisfy heap property. So 4, then 3 and 5 are interchanged, 7. Now, is this heap satisfying shape property? Yes. Is it satisfying heap property? No, because see 4 is not less than 3. So again interchange these two. 4 on 3, 4, 7, 5. See, this is a binary heap we have created. So 3 is less than its children, 4 and 7, 4 is less than 5. Yes, it is satisfying shape property and it is satisfying heap property. So as it is satisfying both the shape property and heap property, we can say it is a minimum heap, min heap. Now insert 2, insert 2. 3 is root element, 4, 7, 5. 2 is inserted at the end of the binary heap tree. So the next possible location is right of 4, 2 is inserted. Now check whether it is satisfying shape. Yes, it is complete binary tree. Is it satisfying heap, minimum heap property? No, it is not satisfying min heap. 3 is less than 4. Yes, 3 is less than 7. No issue. But 4 is less than 5. Yes, but 4 is not less than 2. So interchange these two values. 3, 2, 7, 5, 4. Is it satisfying shape? Yes. Is it satisfying heap? No, because 3 is not less than 2. Again interchange these two. 2, 3, 7, 5, 4. What about shape and heap? Shape. It is complete binary tree. shape, complete binary tree. What about heap? 3 is less than 2 is less than 3, 2 is less than 7. What about 3? 3 is less than 5, 3 is less than 4. Heap properties also. So it is a min heap. Now try to insert next node 10. Insert 10. Insert 10. So we are going to insert 10 at the end of the heap. 2, 3, 7, 5, 4. Next possible location to insert 10 is left of 7 in the level 2. Level 0 is completely filled, level 1 is completely filled, level 2 there is a possibility of inserting an element. So the element is inserted as left of 7. So 10 is inserted. Now check whether it is satisfying shape property. Yes, it is a complete binary tree. Then what about heap property? It should be a minimum heap. Is it satisfying minimum heap? 2 is less than 3, 2 is less than 7. What about 3? 3 is less than 5, 3 is less than 4. What about 7? 7 is less than 10. So all the elements they satisfy heap property also. So this is a min heap. Then insert 11. Insert 11. Already we have 6 elements: 2, 3, 7, 5, 4. Left of 7 is 10. We insert new element at the end of binary heap. So 11 is inserted as right of 7. Now check after insertion of new node at the end of heap, check whether it is satisfying both the properties, shape property and heap property. What is shape? Yes, it is following complete binary tree. Complete binary tree. What about heap? It should follow minimum heap. 2 is less than 3, 2 is less than 7, 3 is less than 5, 3 is less than 4, 7 is less than 10, 7 is less than 11. So it is following minimum heap property. So in this way, we can insert nodes to a binary heap. We can construct a binary heap in min heap fashion by inserting nodes one by one. Every time you insert a node, new node at the end of heap and check with its parent value. You wanted to construct minimum heap, the parent value should be less than the newly inserted value. If it is not satisfying, interchange them and again compare that with its parent, so that all the elements should follow these two properties, shape property and heap property. Of course, we add new node based on shape property only, so no issue. But we have to check every time whether insertion of node satisfying heap property, min heap. So the parent always should be less than its children. All the nodes follow the condition min heap condition. So if it is not satisfying, you have till you satisfy that condition, you have to repeat heapify process so that you can construct a minimum heap in this fashion. Thank you. Let me explain how to construct a max heap using 5, 4, 7, 3, 2, 10, 11. Initially, max heap is empty heap. We need to insert 5. Insert 5. 5 is inserted as the heap tree is null tree or empty tree. This is the first node and that will be your root node. There is only one node in the binary tree, heap tree. It is having, we have to check whether it is following the two constraints, shape property, heap property. Shape should be complete binary tree and heap should be max heap. Max heap means parent should be greater than children value. Here there is only one value. It is only root value, it is having the shape of complete binary tree and it is following max heap also. So it is max heap. Now insert one more value, insert 4. So already 5 is there. You need to insert in the next possible location, that is left of 5, because if it is a complete binary tree, there is a possibility of adding two values, but we have to fill the left value first. So 4. 4 is inserted like 5, 4. This is root value. Again check, is it following shape property? Yes, shape property. Root the next level element is filled from left value. Is it following max heap property? Root is greater than its children. Parent is greater than child value. So it satisfies both the conditions. So this is a max heap. Again insert next value. Insert 7. Now root is 5, left is 4, 7 is inserted as its right. It is complete binary tree. So it satisfies shape property. What about heap property? Heap property means max heap property. Parent should be greater than children. Parent is less than child. So if you identify parent is less than child, interchange them. So interchange. 7 is root value, 4 and right is 5. Now it satisfies shape property and heap property. Now try to insert one more value, 3. Insert 3. Insert 3. Already we have three values, 7, 4, 5. Now we are going to insert 3 as left of 4. There is the possibility of adding only value at the end of the heap, means left of 4. Now it is complete binary tree. It satisfies shape. What about heap? Heap should be max heap. 7 is greater than its children. 4 is greater than its children. Yes, heap is also satisfied. Then insert 2. Insert 2. Already we are having 7, 4, 5, 3 as a left of 4. Next possibility is right of 4, 2. Now check, are they satisfying shape property? Yes, it is complete binary tree. Is it satisfying heap property? Max heap. 7. Parent is greater than its children. Yes. 4. 4 is parent. 4 is greater than its children. Yes. It is satisfying both the conditions. Then insert 10. Insert 10. Now 7 is root value. 4 is its left value. 5 is its right value. 3 is left of 4. 2 is right of 4. Then left of 5 we fill 10. Is it following shape property? Shape. Yes, it is a complete binary tree. Heap property. Heap should be max heap. Is it max heap? 7 is greater than its children, but 5 is not greater than 10. So interchange. So 7, 4, here 10, 3, 2, 5. 10, 5 are interchanged. Now is it satisfying heap property? No. 7 is less than 10. So parent should be greater than 10. Now again interchange these two. 10, 4, 7, 3, 2, 5. Now is it satisfying the heap property? Yes, it is satisfying shape property. Yes, both shape and heap are satisfied. So it is max heap. Now again insert 11. Insert 11. To insert 11, we have already 10, 4, 7, then 3, 2, 5. We can insert element right of 7, which is 11. Now, is its shape property satisfies? Shape? Yes, shape is complete binary tree. Heap property? Heap. It is Is it satisfying max heap? 10 is greater than 4 and 7. Is 7 greater than 5 and 11? No. 11 is greater than 7. So, we have to interchange these two first. So, 10, 4, 11, 3, 2, here 5, 7. Is it satisfying shape property? Yes. Is it satisfying heap property? No. 10. Root should be greater than its children. So 10 is less than 11. So it is not satisfying heap property. So again interchange 10 and 11. 11, 4, 10, 3, 2, 5, 7. Now 11 is root value. It is satisfying shape property. It is a complete binary tree. And what about the second property, heap property? Heap property should be max heap. Max heap means parent should be greater than children. 11 is parent of 4 and 10, greater than 4 and 10. 4 is parent of 3 and 2. So 4 is greater than 3 and 2. 10 is greater than 5 and 7. So it is completely satisfying shape property and max heap property. So in this way, we can construct a max heap using the given values. So every time you insert value at the end of the tree and check the value with its parent value. If the parent value is smaller than this value, interchange them. The process is repeated till all the elements have satisfied the shape property and heap property. Let me explain the algorithm to insert an element into a max heap. Algorithm to insert an element into a max heap. We are going to derive an algorithm for max heap by inserting one element at a time. At any point of time, heap must maintain its property. What is property? Complete binary tree. It is shape property, complete binary tree, and heap property. Max heap. Parent should be greater than children. So it should satisfy these two properties, shape property and heap property. Every time you insert an element, you have to check whether it is satisfying shape property and whether it is satisfying heap property. See the algorithm. Step 1. Create a new node at the end of the heap. We have to add a node at the end of the heap. Assign the new value to the new node. Then compare the value of child node with its parent node, or compare the value of the new node with its parent value. If the value of parent is less than child, swap them. Repeat steps 3 and 4 until heap property holds for all the nodes of that particular binary tree. I will explain this with an example. Example 1. Insert a node with value 10 to the following max heap. There is a max heap. So this is the max heap. 7 root 4 5 3 2. We are going to insert value 10. Insert 10. So we may insert a value. See, first step, create a new node at the end of the heap. At the end of the heap means it should follow shape property, complete binary tree. Complete binary tree means next element that can be added is left of 5. So create a new node at the left of 5. Yes, a new node is created. Then step 2, assign new value. 10 is assigned. Then compare the value of the new node. Compare the value of new node with its parent value. Parent is 5, child is 10. So what is the heap property? Parent should be greater than child. Is it greater than? Is it satisfying heap property? No. So it is not satisfying heap property. So swap these two values. 5 and 10 are swapped. See, 5 left of 5 is 10. So they are going to be interchanged. So 10 and 5. Now check, is it satisfying shape property? Yes, shape property is okay. What about heap property? It is not okay because see here 7 is parent and 10 is child. 7 should be greater than 10. Again, these two has to be interchanged. 10 and 7. 10, 7. Now check shape property. Yes, shape property. It is satisfying shape property. Shape property is complete binary tree. What about heap property? 10 parent is greater than children, 4 is greater than 3 and 4, 7 is greater than 5. So it satisfies shape property and it is satisfying heap property also. So we have inserted successfully one node into a max heap. Now let me explain adding one more node value 11 to the following max heap. Say we have already constructed a max heap. So this is the max heap tree before insertion of node 11. See, this is a max heap 10. Its children are 4 and 7. 4 children are 3 to 7 children is 5. So it satisfies shape property, heap property. Shape is complete binary tree and heap is max heap. Parent is greater than children. Now insert 11. Insert 11. There is a possibility of inserting 11 at the right end of 7. So you may insert 11. So first step, create a new node, add it at the end of the binary tree. Yes, assign the new value 11, whatever the value you wanted to insert, assign there. Then compare with its parent value. Parent is 7 and child is 11, so it is not following max heap property. So interchange these two values. 7 and 11 are interchanged. After insertion interchanging, again check the value of 11 with its parent again. Parent is 10, the value is 11. So again it is not satisfying heap property. Shape is okay, but heap is not okay. Shape satisfied, heap property not okay. So because parent should be greater than children, so again interchange these two. 10 is placed at root and 11 is placed in the root and 10 is placed in the place of 11. Now check, is it satisfying shape property? Yes, shape is complete binary tree. Heap is max heap. See, parent is greater than children. 4 is parent, it is greater than its children. 10 is parent, it is greater than 5 and 7. So max heap. In this way, you can insert any number of nodes to a heap, max heap, or maybe let me explain an algorithm to delete a node from a max heap. We can delete any node from a max heap. It is just like a binary tree. So in a binary tree, we can delete any node. But after deleting the node from a binary tree or a heap, the remaining nodes should satisfy again the two constraints, shape property and heap property. Shape property and heap property. Shape property is a complete binary tree and heap property is max heap. Here max heap. Suppose if we select a max heap and if we have a target node to be deleted, delete that node. After deletion of the node, the remaining node should form again a complete binary tree, that too a max heap. So for this there is an algorithm. So there are sequence of steps. Step 1, replace the value of node to be deleted by the value of last node of the heap tree. So replace with the last node. Whatever the node to be deleted, replace with the value of last node. Then delete the last node. Delete the last node. Now step 3. As the last element is placed somewhere in between as the node to be deleted, it is not following the uh, heap property, max heap. It will not satisfy max heap property. It may satisfy shape property because it is already a max heap. It satisfies shape property, but it is not satisfying heap property. So compare with its children. So if it is smaller than its children, replace the value or interchange the values. So the heapify has to be repeated many times so that all the values of or all the nodes of the heap should satisfy heap property, max heap property. I will explain this with an example. Say this is a max heap. Max heap. See here, it is satisfying shape property and heap property. So shape is just like a complete binary tree, and heap 44 is greater than 42 and 35. Its children 42 parent. Its children are 32 and 31. So greater than children. Then 33 is greater than 11 and 26. 31 is greater than 14 and 35 is greater than 19 and 27. Everywhere parent is greater than its children. Now, if you are asked to delete 44, the first step, replace the value of the node to be deleted. Yes, the node to be deleted is 44. It should be replaced with last value. So 14. So interchange or just replace value of 44 with 14. Then delete last value. Step 2, delete last node. Now it is satisfying shape property, but it is not satisfying heap property. See, 14 is placed in the root position, that is 44 we have to delete. So they are interchanged, last element 44 and 14. Now 44 is also deleted. Once you delete, you will have 14 as its root value, 42 as its left value, 35 as its right value. Of course, it is satisfying shape property. It is not satisfying heap property, because so 14 is root value, it should be greater than its children 42 and 35. So it is not greater than 42 and 35. So if you wanted to make it again a max heap, you have to replace with the largest value, say 42. 42 has to be placed in the place of 14 and 14 will be placed in the place of 42. Again, is it satisfying the shape property? Yes, it is satisfying shape property. Now, is it satisfying heap property? No, because 14 is less than 32 and 31. Again, they will be replaced. The largest value of 31, 33 is 33. So, replace with 33. So 33 will be placed here, 14 will be placed here. Now is it satisfying shape property? Yes. It's satisfying heap property? No. 14. 14 is parent. It should be greater than its children. So 11 or 26. So 11 or 26, it is greater than 11, but it is not greater than 26. Now 14, 26 is placed here, 14 is placed here. Now it is satisfying shape property and heap property. Now this is clearly see here 42 is 42 and 14 are interchanged, then 14 and 33 are interchanged, then 14 and 26 are interchanged, 14 and 26 are interchanged. Finally, you have got a heap where it is a max heap. It is satisfying shape property. Shape is a complete binary tree, and heap is max heap. Shape complete binary means level by level it is filling, first level, second level, third level, fourth level, level 0, level 1, level 2, level 3. Every time the elements are filled from left to right. See, first level completely filled, second level completely filled, third level completely filled, fourth level elements are filled from left to right. Yes, so it is satisfying shape property. Then what about max heap property? Max heap, here we are following max heap. So parent, as far as these two are concerned, 42 is parent, 33 and 35 are children. 42 is greater than 33 and 35. As far as this is concerned, 33 is parent of 26 and 31. So 33 is greater than 26 and 31. 35 is greater than 19 and 27. 26 is greater than 11 and 14. So it is satisfying heap property also. Shape property it is satisfying. Heap property is satisfying. It is that too after deletion of node 44. Right? From a max heap, we are deleting node 44. After deleting node 44, again the remaining elements are readjusted or heapified you to satisfy shape property and heap property. Now see, this is represented an array. The max heap is represented in array like this. See, 42 first root value, then its children 33, 35, then children of 33, 26, 31, children of 35, 19, 27, children of 26, 11 and 14. Elements are filled from level by level. First element, second element, third element, fourth element, fifth, sixth, seventh, eighth, ninth. So in, index 0, index 1, index 2, index 3, index 4, index 5, index 6, index 7, index 8. So there are 9 elements. There are 9 elements. They stored from index 0 to index 8. So elements are filled from level by level, level 0 to level 3. So whatever it may be, say here of course there are 3 levels. Elements are filled from level 0 to level 3. Thank you.